The human body does not have a fixed voltage like a battery. Rather, it operates through electrical signals that vary in voltage depending on the context. Here are some key points regarding the voltage in the human body. Resting membrane potential. Cells, particularly neurons and muscle cells, have a resting membrane potential typically around -70 millivolts. This voltage is created by the distribution of ions, like sodium and potassium, across the cell membrane. Action potentials. When a neuron fires, it generates an action potential, which can reach voltages of about +30 to +50 millivolts briefly. This rapid change in voltage is crucial for the transmission of nerve impulses. Electrocardiogram, or ECG. The heart generates electrical signals that can be measured in millivolts. An ECG typically shows voltages ranging from 0.5 to 3 millivolts during the heart's electrical activity. Electroencephalogram, or EEG, measures brain activity by detecting electrical activity in the brain. The voltages detected can vary, usually ranging from 1 to 100 microvolts. While the human body generates electrical activity, it doesn't utilize voltage in the same way electrical devices do. Instead, these electrical signals are essential for communication within and between cells, facilitating vital functions like muscle contraction and nerve signaling. The human body emits electrons primarily through several biological and physical processes. Here are the key ways this occurs. Metabolism. During metabolic processes, cells convert nutrients into energy. This biochemical activity involves various reactions that can result in the release of electrons. For instance, in cellular respiration, glucose is oxidized, releasing energy and producing electrons. Ionization. The human body contains various ions, which are charged particles that can gain or lose electrons. When these ions interact with each other or with external radiation like UV light, they can emit electrons. This process can contribute to the body's overall electron emission. Thermal radiation. The human body emits infrared radiation due to its temperature, which is around 37 degrees Celsius or 98.6 degrees Fahrenheit. This radiation can carry away energy, including electrons, although this is a less direct method of electron emission. Electrical activity. The human nervous system operates through electrical impulses. Neurons communicate by transmitting electrical signals, which involve the movement of ions and thus electrons across cell membranes. Bioluminescence. While not common in humans, some biological processes in other organisms can emit light through the release of electrons in biochemical reactions. This phenomenon is not a significant source of electron emission in humans. Overall, while the human body does emit electrons, it is part of complex biochemical and physical processes, rather than a direct emission like a charged particle beam. The human body, as a bioelectrical system. Faraday's electrochemical principles and biochemistry. The human body is a fascinating biological entity that operates through intricate electrical activities. These activities can be symbolically and scientifically related to Faraday's electrochemical processes, illustrating how our body functions similarly to electrical devices. By examining the biochemistry of the human body, particularly the behavior of electrons, we can draw parallels to Faraday's law of induction and the principles governing linear induction motors. Faraday's law of induction and the human body. Faraday's law of induction states that a change in the magnetic environment of a coil of wire will induce an electromotive force, or EMF, in the wire. This principle underpins much of modern electrical engineering, including the operation of generators and transformers. The human body, while not a coil of wire, similarly generates and utilizes electrical energy through biochemical processes. At the cellular level, the human body generates electrical activity primarily through the movement of ions across cell membranes. This movement is essential for various physiological processes, including nerve impulses and muscle contractions. Resting membrane potential. Cells maintain a resting membrane potential, typically around -70 millivolts, through the active transport of ions such as sodium and potassium across their membranes. This process is akin to establishing a voltage difference, much like a battery. Action potentials. When a neuron fires, it undergoes a rapid change in membrane potential, known as an action potential. This involves the influx of sodium ions followed by the efflux of potassium ions, creating a temporary positive charge inside the cell. The action potential can reach voltages of +30 to +50 millivolts, similar to a current-carrying wire experiencing voltage changes. The behavior of electrons in the human body is governed by complex biochemical reactions. These reactions involve the transfer of electrons, which is fundamental to processes such as cellular respiration and ATP production. Cellular respiration. During cellular respiration, glucose is oxidized and electrons are transferred through a series of proteins in the mitochondria, known as the electron transport chain. This transfer process generates a proton gradient that drives the synthesis of ATP, the energy currency of the cell. Ion channels and pumps. Ion channels and pumps in the cell membrane regulate the flow of ions, creating electrical signals. For example, the sodium-potassium pump actively transports sodium out of the cell and potassium into the cell, maintaining the resting membrane potential. The human body's generation and utilization of electrical signals can be symbolically compared to current-carrying wires and voltage induction in electrical devices. Just as Faraday's law describes the induction of EMF in a coil due to changing magnetic fields, the human body induces electrical signals through the movement of ions and the transfer of electrons, neural transmission. In neurons, the propagation of action potentials is analogous to current flowing through a wire. The sequential opening and closing of ion channels along the axon resemble the switching mechanisms in electrical circuits that regulate current flow. Muscle contraction. Muscle cells generate electrical signals that trigger contraction, similar to how electrical devices use current to perform mechanical work. The influx of calcium ions in muscle cells initiates the interaction between actin and myosin, leading to contraction. Linear induction motors and human electrophysiology. Linear induction motors operate based on the principles of electromagnetic induction, where a moving magnetic field induces a current in conductors. Similarly, the human body relies on the induction of electrical signals to coordinate various physiological functions. The nervous system uses electrical impulses to communicate between different parts of the body. These impulses are induced by changes in ion concentrations and membrane potentials, much like the induced currents in linear induction motors. The heart's electrical activity, measurable by an electrocardiogram, ECG, results from the coordinated induction of electrical signals across cardiac cells. This induction ensures the rhythmic contraction of the heart, pumping blood throughout the body. The human body's ability to generate and utilize electrical activity is a remarkable example of biological processes that mirror electrical engineering principles. By examining the biochemistry of ion movement and electron transfer, we can draw symbolic and scientific parallels to Faraday's law of induction and the operation of linear induction motors. Understanding these connections enhances our appreciation of the intricate electrochemical processes that sustain life and highlights the profound integration of biology and physics. Electronic human detection sensors, advancements, and applications. In an era increasingly defined by technological innovation, electronic human detection sensors have emerged as pivotal tools in various fields, ranging from security and healthcare to smart homes and robotics. These sensors leverage advanced technologies including infrared, ultrasonic, and image processing techniques to identify and track human presence and movement. This essay explores the principles behind electronic human detection sensors, their applications, and the implications for society. Principles of electronic human detection sensors. Electronic human detection sensors operate based on several underlying technologies, each suited for different environments and applications. The most common types include passive infrared sensors, or PIR. These sensors detect the infrared radiation emitted by human bodies. When a person enters the sensor's field of view, the change in infrared levels triggers the sensor, activating a response such as turning on lights or an alarm. Then we have ultrasonic sensors. These devices emit ultrasonic waves and measure the time it takes for the waves to bounce back after hitting an object. If a human moves within the sensor's range, the change in the returned wave pattern indicates their presence. Microwave sensors are similar to ultrasonic sensors. They emit microwave signals and detect changes in the reflected waves. They are often used in applications requiring longer detection ranges. Next, we have video and image processing. Cameras equipped with advanced algorithms can analyze visual data to detect human shapes and movements. This technology is increasingly used in security systems and smart home applications, enabling features such as facial recognition and behavior analysis. Lastly, LiDAR sensors. LiDAR systems use laser beams to create detailed three-dimensional maps of the environment. They can precisely detect human movement and position, making them valuable in autonomous vehicles and robotics. Applications of electronic human detection sensors. The applications of electronic human detection sensors are vast and varied, reflecting their versatility and adaptability. Security and surveillance is one of the primary uses of human detection sensors. Motion detectors trigger alarms or cameras when unauthorized movement is detected, enhancing security for homes, businesses, and public spaces. Advanced systems can differentiate between humans and animals, reducing false alarms. In smart homes, human detection sensors are integrated into lighting, heating, and security systems. For example, lights can turn on automatically when a person enters a room, and thermostats can adjust based on occupancy, contributing to energy efficiency. In healthcare monitoring, electronic sensors play a crucial role in patient monitoring. Wearable devices can track vital signs and detect falls, alerting medical staff when immediate assistance is required. Similarly, sensors in hospitals can monitor the movement of patients, aiding in their safety and care. Robotics and automation also benefit from human detection sensors. They are integral to the development of robots, particularly in applications where interaction with humans is necessary. For instance, service robots in hotels or restaurants use these sensors to navigate surroundings and assist guests. Retail and marketing sectors employ human detection sensors to analyze customer behavior, optimizing store layouts, and enhancing marketing strategies. By tracking foot traffic and dwell time, businesses can make data-driven decisions to improve customer experiences. Implications for society. The proliferation of electronic human detection sensors presents both opportunities and challenges. On one hand, these technologies enhance safety, convenience, and efficiency in everyday life. They enable smarter cities and more responsive environments, contributing to improved quality of life. For instance, smart traffic systems can adjust signals based on pedestrian and vehicle presence, reducing congestion and improving safety. On the other hand, the widespread use of these sensors raises concerns about privacy and security. Continuous monitoring can lead to data collection without consent, potentially infringing on individual freedoms. As such, it is imperative that developers and policymakers establish guidelines to ensure ethical use of human detection technologies, balancing technological advancement with respect for privacy. Electronic human detection sensors represent a remarkable intersection of technology and human interaction, offering significant benefits across various domains. From enhancing security and enabling smart home functionalities to improving healthcare monitoring and retail strategies, these sensors are transforming how we interact with our environments. As technology evolves, it is crucial to address the ethical considerations surrounding their use, ensuring that advancements serve to improve society while safeguarding individual rights. The future of electronic human detection sensors promises to be both innovative and impactful, shaping the way we live and work in profound ways. The concept of utilizing electronic systems to interface with human brain electrical signals for controlling mechatronic devices is a fascinating intersection of neuroscience, engineering, and advanced robotics. This essay explores the types of electronics that can facilitate this interaction, the underlying principles, and the potential applications of such technologies. Brain-computer interfaces, or BCIs, are systems that enable direct communication between the brain and external devices. They operate by detecting and interpreting neural activity, typically through electroencephalography or EEG, or other neuroimaging techniques. The goal is to translate brain signals into actionable commands that can control devices, such as robotic limbs, computer systems, or even levitating platforms. Types of electronics for neural signal detection and processing. Electroencephalography, or EEG systems, measure electrical activity in the brain through electrodes placed on the scalp. By capturing brainwave patterns, these systems can identify specific thoughts or intentions. EEG signals can be processed in real time to control mechatronic devices, allowing users to manipulate electronic systems through thought alone. Neural signal amplifiers enhance the weak electrical signals from the brain, making them more detectable and interpretable. This is essential for accurately capturing the nuances of neural activity. Amplified signals are fed into processing units for further analysis, enabling the translation of brain waves into control commands. Microcontrollers and field-programmable gate arrays, or FPGAs, can be programmed to interpret the processed neural signals and execute commands based on predefined algorithms. These devices can manage the operation of mechatronic systems, ensuring that responses to brain signals are timely and accurate. Wireless communication modules using technologies like Bluetooth or Wi-Fi facilitate remote communication between the brain-computer interface, or BCI, and mechatronic devices, allowing users to operate them without physical connections. This enables mobility and flexibility, which is critical for applications like wearable technology or robotic systems. Efficient power management systems are crucial for sustaining the operation of BCIs and mechatronic devices, especially in portable or wearable configurations. Systems that harvest energy from the environment or utilize advanced battery technologies ensure long-term operation. Mechatronic devices and electromagnetic forces. The concept of a mechatronic device capable of levitation through electrical energy involves several key principles. Electromagnetic levitation generates a strong electromagnetic field, creating a repulsive force that counters gravity. This can enable the levitation of objects significantly heavier than the device itself. Such technology could allow for the development of advanced transportation systems, personal mobility devices, or even dynamic assistive devices for individuals with mobility impairments. A system of sensors can create feedback loops for control that adjust the electromagnetic force based on the user's neural signals, ensuring stability and responsiveness. This could lead to devices that dynamically adjust their position and orientation based on the user's intentions or movements. Incorporating biometric coordination with sensors that monitor the user's joint movements and body segments can enhance device responsiveness. This integration would allow the mechatronic system to adapt to the user's physical state, improving usability and safety. Potential applications and implications. The integration of BCIs with advanced mechatronic devices has vast potential across various fields. In healthcare, individuals with disabilities could control prosthetic limbs or wheelchairs through thought, providing greater independence. Devices could aid in physical therapy by responding to the user's neural commands, promoting engagement and recovery. In defense and security, enhanced body armor with integrated BCIs could allow soldiers to control drones or robotic systems remotely, improving operational efficiency. Mechatronic systems could be deployed in hazardous environments, operated through neural signals for enhanced safety. In consumer technology, personal devices that respond to brain activity could create more intuitive and personalized living environments. Virtual reality systems could be controlled through thought, enabling immersive experiences. Conclusion. The fusion of electronic systems with human neural signals to control advanced mechatronic devices represents a significant leap in technology. As research in BCIs and robotics progresses, the possibilities for applications expand dramatically, ranging from healthcare and security to consumer technology. The challenges ahead involve not only technical innovation, but also ethical considerations regarding privacy.